Hello and welcome to an introduction to the interactions between the ocean and our atmosphere by me, Jo Wakeham. During this film we will be exploring the interactions between oceanic and atmospheric processes and what effects these have on our global climate and weather systems, which drive the movement of oceans and maintain an inhabitable environment. The key aspects we need to look at to explain some of what's happening between the ocean and our weather include the effects of our solar system and the thermodynamics of the atmosphere, Coriolis force and wind systems, and how these link to waves which produce currents that drive global movement of water, which regulates heat and gases on Earth. This film aims to briefly guide you through each process as we explore the how, what and whys. So let's get started. Earth's relative position to the Moon and Sun within the solar system dictates just the right temperature, and it is linked directly to solar radiation from the Sun, which is the energy force that drives atmospheric motion. Global atmospheric circulation is caused by the Earth's rotation and differential heating. The amount of solar radiation that reaches our aquatic and terrestrial environment is dependent upon factors such as absorption by clouds, scattering by atmospheric gases, and the reflectivity, or albedo, of surfaces. The ground surface conducts sensible heat to the air, where it is moved by convection plumes and wind. This is followed by latent heat, which is carried through evaporation, then condenses, forming clouds. Luckily, clouds cover around 66% of the Earth's surface and play a big role in deflecting away solar radiation. The spherical nature of the Earth also dictates the amount of radiation or insolation that is exposed to a particular area across its surface. Less direct heat reaches higher latitudinal areas than the equatorial regions as a result of the radiation having to travel further through the atmosphere and the surface area it reaches being larger due to the curvature. There are four factors that contribute to the horizontal movement of air, those being centripetal acceleration, frictional forces, pressure gradient force, and Coriolis force. Let's look at those last two. The equator sits on the widest point of the Earth. This area spins faster than the polar regions due to covering a greater distance, and this creates the Coriolis force, which affects particles in motion travelling from a faster moving region to one moving more slowly, deflecting them to the right in the northern hemisphere and left in the southern hemisphere. So what does that mean? Well, movement is created by variations in surface heating from solar radiation, which generates a horizontal pressure gradient that changes the pressure and density of air. Winds are generated by horizontal pressure differences, which drives the movement of air from areas with a higher to lower pressure gradient. Temperature, water content, and height affect air pressure, which drive those winds. Low pressure is caused by warm air rising. These areas have higher rainfall, like the UK and the rainforests. The opposite happens where the air falls, creating higher pressure climates. So, when these factors come together, how are the global winds and circulation cells affected? In this diagram, the Hadley cell shows the movement of warm air rising in the low pressure zone of the equator and moving poleward where it cools, falls and gets transported back towards the equator. The Ferrel, Hadley and polar cells create their own semi-permanent areas of high and low pressure. The three cells contain their own prevailing wind systems, and the pressure systems create weather, which plays a big role in the water cycle. What next? The atmosphere is made up of layers, with the majority of weather happening within the troposphere, which is capped by the tropopause, as seen in the diagram. It prevents the warm air in the northern hemisphere Hadley cell from rising any further. The overall motion results in steady winds across the ocean known as the trade winds. So, the Sun sends us heat, the Earth and atmosphere moderate and redistribute the energy around the globe, which creates pressure changes and winds in our sky. What next? Well, just like blowing on your hot soup to cool it down, semi-permanent surface winds create waves. Wind creates the smaller ripple-like capillary waves, chop, and swell, commonly found at sea, and then cease waves, which are known as standing waves. Mass movement creates tsunamis. The moon and sun create tidal waves. The diagram shows the path of the surface wind travelling over the water body. The frictional stress between air particles moving over water molecules passes energy and momentum from one to the other. The wind stress over a water surface causes a wave to form. Wave refraction is when the lower part of a wave reaches shallower water and slows due to friction, whilst the top moves faster. As a result, waves tend to swing parallel to the benthic contours and ultimately focus their energy on headlands as opposed to open bay areas, leading to erosion and deposition along the coast. Wave energy is dispersed through heat transfer, kinetic and sound energy when it crashes onto the shore. What else do we know about waves? Well, waves can increase in size as they travel over uninterrupted bodies of water. When the wind remains constant, the distance of this is called fetch. Swell are larger continuous sets of waves that have travelled a great distance from their origin, and we use the Beaufort scale to measure a given sea state created by wind and wave patterns. So, what are tides? Tides are waves caused by the gravitational force of the sun and predominantly the moon. The alignment of the sun and moon create the largest tidal range due to the overall increased gravitational pull. The rotation of the earth creates the high and low tide. As the earth spins, it moves through the raised areas of water. Dynamic tidal theory takes into consideration all of the physical elements affecting tidal motion, such as landmass and additional gross forces such as Coriolis. Now, how does this differ to the production of gyres? Long-standing or prevailing winds create surface currents, which are streams of moving water. Collections of surface currents produce gyres, circular moving bodies of water found in ocean basins. The Coriolis effect causes these currents to build up in volume towards the centre, which creates a pressure gradient and an uneven sea surface. Let's explore this further. In the northern hemisphere, prevailing winds that blow parallel to the coastline combined with the Coriolis effect result in a surface current that runs at 45 degrees to the direction of the wind. The frictional dragging force of sub-level layers of water has a knock-on effect that creates a spiral of movement known as the Ekman spiral. This generates the Ekman current, which occurs in the top tens of metres of the ocean and travels 90 degrees to the right of the original wind. Alongside the pressure gradient, these factors combine to generate the coastal Ekman upwelling and downwelling. Where this build-up occurs, it drags water away from the coastline and the moving water is replaced by upwelling of cooler, subsurface water, bringing with it lots of nutrients. These nutrient-rich waters now sit in the epipelagic zone, which is shallow enough to allow sunlight to penetrate through to where photosynthetic plankton can use the sun's energy to grow and create the biomass required to drive the base of the marine food chain. This is known as primary production and has a huge biological importance. Just like the winds, ocean currents are driven by density and temperature differences. The collective term for this movement of water across the oceans is thermohaline circulation. Upwelling and downwelling form the ocean's vertical currents. Alongside the two main current systems, surface circulation, which is wind dependent, and deep circulation, which sweeps along the deep sea floor. The Gulf Stream, one of the Earth's largest and fastest currents, forms at the equator, where the higher concentration of sun results in a greater evaporation rate and higher salt content in this area. Southeast trade winds drive the warm, less dense surface water northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius. The rotation of the Earth and west winds directs the Gulf Stream towards Europe, where it splits up into three directions. The northern flow releases heat into the atmosphere, where the temperature drops and evaporation occurs, leading to the density increasing, and then the water sinks downwards between Greenland, Norway and Iceland, forming underwater waterfalls known as the chimneys. So what have we learned? Processes in the atmosphere create differential impact to our global currents depending where in the world they are situated, and these processes, which redistribute heat, gases and nutrients, are fundamental in driving the global geochemical circulation that maintains our environment and keeps the Earth stable. It appears that what happens in our skies is mirrored by what happens in the ocean. The solar and atmospheric systems drive the weather, and climate systems which drive the oceans, which redistribute water and oxygen to the atmosphere and continue the cycle. So one drives the other, which drives the other, which drives the other, which drives the other. My question is, if one stops, do they all stop?